Okay, good. Then let's get started. Today, we're just going to look at some very simple image manipulations and blob detection, color detection, because those are the algorithms that lots of people think of first when they talk about computer vision. And we will see the drawbacks of those algorithms. So I have a little image here that I took. I guess that's why it's pretty big. I think it was one of the hiking trips with the department. So it's the TRA station. And now I simply loaded that image into my program here using one of the functions that I wrote for the lecture slides. Now for you, you can actually just paste the URL directly into the image reader or download the file first and then run it locally on your computer. Then we load up our set of standard libraries that we use most of the time. In particular here we're loading the OpenCV2 library. So OpenCV is a popular, powerful library. It's used in many different projects. It covers a whole host of different vision tasks, from low-level processing to high-level tasks such as face detection using neural networks or filter cascades. Now, when we actually have an image like this and we want to process it on our computer, then what we get is a two-dimensional array, because we have rows and columns of what's called picture elements, so-called pixels. Now the 2D array is stored in row major order, which means that the columns are changed first. So you have the first row, then the second row, the third row, the fourth row in memory. That information is important because if you want to process your images in real time, if you want to process them efficiently, then you have to know how the image is laid out in memory so that you can make use of cache coherence. If you read one pixel in an image and you want to do some processing and you read this pixel here, the CPU will actually load the next couple of bytes into the level 1 cache, which means that if you read this pixel and then you read this one and this one and this one, then your program is going to run very efficiently because all those pixels are already in the cache memory. If you take your image and you process it up and down, so you move along columns, then you will read this pixel, the computer is going to read in all of those, but then you're going to read the pixel below, which is at a totally different location in memory. So most likely it won't be in your level 1 cache. Eventually the pixel is, the row above is going to be ejected from the cache, which means that when you access the next pixel on that row, you have to reload it. So that is a lot of memory transfer overhead that you just introduced into your program. So most of the images are stored in row major order. So that means that you're always better off to go along rows, one row at a time, instead of going up and down. If you really have a task that requires you to move up and down in memory. It's often faster to rotate the image by 90 degrees to apply your algorithm so that it's now following the rows, and then after you're done with your processing, to rotate the image back by 90 degrees. The most common formats for pixels is the RGB format, stands for red, green, blue, which gives you an additive color model. So you get the amount of red, the amount of green, and the amount of blue in your pixel. Most camera hardware or displays, nowadays those are 24-bit, so 8-bit per channel. The different colors arrays are called channels. And sometimes you can also request an ARGB format, which is then 32-bit wide. That has some other advantages. Often the processor is faster when it accesses memory that is aligned at 32 bits. That was true for a long time, but now with the latest Intel, that's not an advantage anymore. I'm not sure about ARM and AMD. And also, usually the A stands for alpha channel, or transparency of the pixel. So this is really intended for graphics where you want to overlay different shapes and you want it to see through. But for camera and computer vision, that format I actually like, because the camera, of course, doesn't give you any transparency. It doesn't know anything about objects being transparent. It simply gives you RGB values, and A is always set to 0. So that gives you 8 bits that you can use in order to very efficiently mark pixels. For example, if you have visited them before, if they could belong to the ball color space, or the color that represents a ball, if they are part of a horizontal line or a particular feature that you're looking for, like a face, then you have 1 byte of scratch memory that you can use to store some information, which is quite useful sometimes. There's other pixel formats. We'll discuss those later. Some cameras allow you a 16-bit pixel format. So instead of 24 or 32 bits, you now only use 16 bits. Red, green, and blue. Now the 16 doesn't divide evenly into 3. So that particular format, you have 5 red pixels, 6 green pixels, and 5 blue pixels. Bits. 5 red bits, 6 green bits, and 5 blue bits. Then there's HSV, which is a color space that is modeled after human perception, and the goal was to come up with a color space that more closely resembles what humans actually see in an image. For computer processing, computer vision nowadays, I don't think it's that useful anymore, because as we'll see in a little while, most color spaces are really bad. The human visual system is extremely good at processing images and sort of smoothing out the colors, applying the correct colors. The brain understands about shadows and highlights, so that if the color moves into a highlighted area and the brightness increases of all the pixels, then your brain actually compensates for that and makes it look like a single color. But we don't really know how that works, and computers cannot really do that. Which is why the color-based processing, color-coded environments are useful in the beginning, but nowadays we look much more for structure, corners, edges, lines, line segments, circles, shapes in the environment that we can match to a location. And then those can be black and white, and the color information is already removed. There's YUV, which is a special color format that was used by television for television transmissions. That one has the color signal mixed up into a brightness value Y, and then a reddish and a blue component of the pixel. So how much of the color is of that brightness belongs to the red channel as opposed to the blue channel. So let's have a look and see what we can do with our image. So I downloaded the image, it's image 1, and I can get the file name. In my program you can just paste in the file name here, and OpenSea will open the image and read it and put it into memory. And then because I'm running this on the Google Colaboratory, which is not very fast, I will scale down the image a little bit from its very large format. So actually, let me make that a little bit smaller. What is the image size here? Yes, so that's a 4K image, 3648 by 2736 pixels. So that's a very big image, so we don't want to process that. So we resize it to 800 columns and 600 rows. So this is width and height that we specify here. And I'll make it even a bit smaller, 600 by 450, something like that. So then I can display that image using IMShow in Matplotlib. And that's what we're doing here. And then let's see what we get. Oh. Forgot to run this one. And here's the image. And if you look at it carefully, then what do you realize? What's the problem with that image?
The color.
The color, yeah. And what's wrong with the color? The pylons here, for example, are wrong. If you compare it to the original image, those are pylons, so they should be red. The jacket of the person here should be red. This should be red. Everything else looks okay. The geometry looks okay. It's just the colors that are messed up. And this is a common problem when dealing with images. And it's related to the endianness of your processor. So some processors are what's called little endian, like the Intel. Other processors, like the Motorola 68000, are big endian, and some processors can be changed. So the modern Intel CPUs, I think they can run in both modes. Or the latest ARM cores. Now, the endianness defines how multi-byte data is stored in memory. So if you have a pointer to a 32-bit integer, it defines which bits are, then you need 32 bits, so you need 4 bytes, right? So your data is going to be in pointer, pointer plus 1, pointer plus 2, pointer plus 3. The endianness defines where the most significant bits are located and the least significant bytes. So if it's a little endian processor, then at your pointer you're going to have the last byte in your number. So if your number is in decimal 1, 2, 3, 4, then a little endian processor would store that in memory as 4, 3, 2, 1. A big endian would store it as 1, 2, 3, 4. Now, the problem that occurred here is that we're accessing 24 bits, and the OpenCV library expected RGB images, but what we actually got from the image read is when we pass it to Matplotlib, what we actually got is a BGR image, because it was expecting a little endian data stream. So we need to switch the image from RGB to BGR format first before we do any kind of processing. And you need to do this for every image that you that you want to show using OpenCV. Now, what we need to do is we have 3 bytes. The first one tells us the red color component. The second one is the green color component. The third one is the blue color component. And we need to swap those around. So all the bytes, the blue has to move into the red, and the red has to be swapped into the blue. Now, of course, you could do this with loops, but the NumPy arrays have a pretty powerful feature, a very powerful feature, that allows us to subslice and index images. And this one line is actually all that is required in order to swap the red and the blue channel. And what it says is that for every row, so we have a colon here, which means every row, and every column, so that's the entire image. The last component of our image is the actual pixel, and there I want to iterate over the entire range from 0 to 3, indexing it with -1, which means reversing it. And then we can run it. And now our image is correct. So now you can read in images, and then if you want to apply edge detection to it, then you can do that. If you want to apply histogram of oriented gradients to it, then you can do that. The colors now will be correct. Sometimes, if this is only for a robot, you may just not bother to swap the colors, or if you need to convert it into grayscale, then technically you would need to do that. We'll talk a little bit about the lightness response of the human eye. But converting it into grayscale, you can often get away with just using a very simple, more hacky method, but okay. So now we talked about the different color channels, red, green, and blue. So for that image, let's just have a look and see what that looks like. So what I want to do is I want to extract the different color channels. So I get red, green, and blue. Now each one of those is going to be a 1 byte entry. So that means now I have a grayscale image. There's no more color information. I have 3 grayscale images. One for red, showing how intense the red component is in different parts of the image. One for green and one for blue. And those are given using the index here, 0, 1, and 2. So I'll take the image, convert it, map it to a grayscale, and then show the red channel, the green channel, and the blue channel. And here's our output, the green channel. Let me open the image. Then here, very bright response, right? In the red channel for the pylon and the person, average in green, and then the blue is a little bit too far out, but you can see the blue channel there. So if there was a blue truck, like they're popular in Taiwan, then that would show up bright in here. So now let's take the plane and extract the map, and then I want to compress it. So I call that function to map the plane. So for the plane, I extract that plane from the image. So index here should be 0, 1, or 2 for red, green, and blue. Then I calculate the maximum and the minimum of that data and the average of that plane. And then I print out the color that I'm processing and the maximum and the minimum and the average brightness over the entire image for this one color channel. And then I update the plane. I replace it by subtracting the average and dividing it by my compression factor. So basically I take the signal, and before, if my plane may have had values from 0 to 255, if I and the average at 64, for example, then now I compress everything by a factor of 4, which means that the values is going to be from 64 minus 128 divided by 4 to 0 and up to 128, but not more than that. Then I calculate the new features, so the new maximum, the new minimum, and the new average. And then I write that plane into the image. So now I've basically taken, with this function, I've taken the full range of brightness response in a particular channel and now squashed it together so that most of it is going to be blurred out. Oh, excuse me. So here's the output of our processing if we compress it by a factor of 2, green by 4 and blue by 32. So let's just compress it by 2 first. So here we have the red channel, the green channel, and the blue channel after it has been compressed. So before, the red channel was from 73 to 198 with an average of 142. Afterwards, it has an average on 141, so the brightness didn't change. The average brightness didn't change. But now the minimum value is 107 and the maximum value is 169. Similarly for the green channel, which went from 104 to 167 to 120 to 152, also with roughly the same average. And the blue channel, which went from 133, 141 to 134 to 138, with also an average that is roughly the same. So here's our 3 channels. Now, of course, what we want to do is combine them together to see what the image looks like. So here I take the image and I pick one of the channels and compress it by 2, and the other ones, I take all the channels, compress it by 2, and then show what the result looks like. For 255, 73, 188, so that's what we calculated before. And then I compose the image back. But so this is for all 3 channels, 1 channel separate. So first I compress red only, put it back together as one image, then green, then blue. So here only the red channel is compressed. Here the green channel is compressed, and here the blue channel is compressed. And this one now looks Okay, in this case, for this particular image, the red channel actually had the least artifacts. I think green shows a lot of changes, and blue also changed, especially the color of the sky. So we can see that the human visual system actually is much more attuned to the green color than to any other color information in the world. If somebody modifies just a little bit in the green color range, then you're going to notice this very quickly. If they modify in the red and the blue, then that's much harder to detect. And in fact, people talk about blue blindness because the blue channel can actually be compressed many times more, and you don't really see any changes in the image. So let's do that again. Except now I compress the image by a factor of 400. So what that will do is it basically takes the image and cuts out the red plane and just replaces it with the average red color. And similarly for the green, and similarly for the blue. Okay. How come no more I am read? And the image that I wanted to use is that image from our robots. Yeah. So CV2 that I here is none. So why did this? Yeah, there's the image. Why doesn't it like that one? Okay, then let me download the image with my functions. Okay, so here we have the direct link. Isn't it get default file name? Oh, string. Okay. So here red has some artifacts, green a lot of artifacts, blue is actually almost indistinguishable from the original image. But as you can see in this particular image here, we replaced the entire blue channel with just a single color, like it goes from 120 to 121. So there's extreme little variation. Since they are bytes, that means they must be integers, so we only have two values. 120, we only have one value basically, 120 and 120 and 121. The other ones are compressed similarly. So this shows, oh, I cannot run that right now. This shows an interesting feature of the human visual system. In spite of what we think, we're basically blind in the blue color channel. I think the reason for that is that if you think about nature, there's actually very few blue things that we need to watch out for. We need to see trees and grass, things like that. Blood, red, I guess, is also very important for survival, but there's very few blue things in nature, apart from the ocean and the sky, but that one is sort of background. There's not much information that we need to extract out of the sky. If you want to predict the weather, you'd be looking at clouds, but not the blue parts of the sky. Let me just run that one more time. Okay. Now, one application of this is the realization that when you looked at the image, you didn't see anything weird as far as the colors are concerned. So our brain, for these images like that, we can see the colors and the shapes and everything. Our brain fills in a lot of the information about the lighting and shadows and things like that in order to give us a consistent view of the world that we can deal with. Now, in order for our brain to be able to do that, it needs to come up with a world model. But of course, there is an infinite number of possible world models. So somehow, in order to be able to process the environment fast enough, our brain needs to be able to pick the likely models. And it's very good at that. As long as the scenes are natural, we extremely rarely do even children make mistakes. But if it's a natural scene, or if it's a deliberately constructed scene, then our brains are easily fooled, and then that's what would lead to optical illusions. Talked about face recognition of their parents. So the brain can easily be fooled by artificial images. Especially when it's scenes that don't occur often in nature, then the brain often gets confused. And then this is what's called an optical illusion. So let's have a look at some of my favorite optical illusions. Which explains some of the difficulties of dealing with images. So these are all advanced ones. Where's the one? These are all patterns that swirl around when you focus on one part. I wanted to have something a little bit simpler. So this is a very cool one. If you look at this picture, then what does your brain tell you about the color of square A and square B? Well, most people will say that A is dark and B is white or light. Here's our image, and let me swap the view. So here we look at the colors. Now when I actually take a color picker, where's that here? Let me try this one. And say I want to have this color here. Then it actually also maps around this color here. It selects this color as well. Here's the color picker. So this color picker is selected, and my color selector, does it show the this drawing program uses HSV, by the way. Tool options. Yes, layers. I thought there was a... No. It doesn't actually show the RGB, but when I click on this and this, then you see that the actual color here doesn't move. So this in fact is the same color. So now the question is, why does that happen? Well, what fools your brain in this case is that this picture is artificially generated. It's not one from nature, but it uses cues that your brain understands how to interpret. And here we have a cylinder that casts a shadow. So the brain would say, if this and this is the same color, then since this is in the shadow, it should be darker than this part here, which is in the sunlight. So in order for them to be the same color, these two have, this one has to be white and this one has to be darker because it's in the sunlight. So the 3D geometry of the image makes an impact, but we can look and see how we can modify the image in order to see how big of an impact it actually has. So let me just take the image and I didn't want to use that color, did I? I want to here I can actually crop the image first. So instead of looking at the entire image, let's just look at this part and this part here. And now, even if I just look at those two, that effect is still very strong. It's a little bit less, but B still is white, A is still dark. Then I can zoom in even more. And now it's already a little bit more washed out. And if I want to convince you that it's the same color, then what I can do is I can draw a path. So here's the color, here's my brush, make it a little bit smaller, 20. And now I can just draw from here to there. And now when I draw this line, now your brain says, no, absolutely, those two are exactly the same color. Like you can actually see it switch, right? If I draw, nothing yet, nothing yet, nothing yet. Now we touch, now all of a sudden your brain goes, oh yeah, same color. What's interesting is that they have done studies in the optical nerve and the eyes of people, and your eyes actually are correct. Your eyes tell the brain that these two are the same color, but your brain just says, oh, you've been lying to me all this time. I can't trust you, so I know what this looks like. And definitely A is dark and B is white. And that's how you perceive that particular image then. So this is a very profound effect, very strong effect, even using a very simple image with just two colors, basically, black and white. And it's very easy to fool your brain. Now the other one that I like a lot, oh, I didn't switch. Okay, that didn't switch on. Yeah, so this is what it should look like. Wait. So here, let's go back. This is what I did to the image. I think you missed it. Here's the image, and then we selected some colors. No, it doesn't like that. So first thing that I did was crop the image. So you can see when I get rid of this part and this part, then the effect is still pretty strong. You still see that B is white and A is black. Then I can also crop away no move. Then I also crop this. Even if I get rid of all the other parts of the image, then your brain still thinks B is white and A is black. And now, if I actually want to convince you, then I simply have to go to the color picker, pick the color, and then I draw a line from A to B. And now you can watch what happens. So I draw, and nothing yet, right? A is still dark, B is still white, and as soon as I connect, a little bit too far, now B and A are definitely the same color. So your brain sort of says, okay, fine, now I believe you. Another very cool illusion is this one here. Oh, no, that's not the one that I wanted. Ah. Create a new image. So here's another optical illusion that also plays on the shading of colors due to lighting and shadows. Now this one works extremely well if you have an overhead projector, because then I can just put my arm between the two and you'll see that the color turns instantly into the same color. I cannot put an arm here, but I can draw one. So let's pick any color. Okay, and now let's pick some green like this maybe, and then see what happens when I blot out this part. And now, tada, magically the two blobs turn into exactly the same color. The up and the lower part. Now your brain doesn't use the implied cues from shadows and highlights of the three-dimensionality of the scene, and it just looks at the colored blotches and it says, of course those are the same color. If you give it, I didn't do any magic on the image, of course. If you just look at the color now, then you'll see that you're convinced this is white and this is black. So there are some very cool ones, but basically it's when shortcuts in your brain fail. Okay, so that's the first lesson that looks at OpenCV and some very simple manipulation of images. Now let's have a look at blob detection and color detection. I want this one. Okay, somebody send a message. Any problems with the stream? No. Okay, good. So when we started working on robotics, for example, then we thought the easiest way to make sure that our robots understand the environment is to color code the environment. So we used orange ball and a green playing field and white field lines and a blue goal and a yellow goal. And the teams were wearing vests in cyan and magenta, which sort of spreads out the color space as much as possible. But it turned out that this is extremely difficult on a larger playing field. This works if you are dealing with a relatively small workspace where the lighting is uniform. If you can control the lighting, like in our lab, for example, if the lighting is not is too dark in one corner of the playing fields, we could just install extra lights there. But when we go to the competition, then that's not possible anymore. But in the mid 1990s to early 2000, people were spending a lot of time then trying to calibrate colors in order to get the perfect color model for what the orange ball would look like or what the yellow goal would look like. And as soon as somebody opened a window or turned on the light, then all the teams had to completely recalibrate their colors. It was a nightmare. Like, we had at that time 3 setup days, and basically 80% of the time we would be just calibrating colors over and over again. We'll see why color, even though you think it's a very strong feature and a very easy feature to detect, why that turns out to be quite difficult in reality. So let's look at the simplest problem we can do with our computer vision system, trying to detect a ball of a particular color in our environment. A soccer ball, yellow tennis ball, something like that, basketball. More messages. Right, and I will have to go to automatic and okay. Yeah, so here's a computer vision application that you may consider that would be interesting in doing. More and more cities and communities all over the world are concerned about the fact that the birds, especially the singing birds, are disappearing. Their population keeps declining. So they have different methods, bird feeder houses, noise reduced roads, barriers over bridges and things like that in order to try and help the birds, but they would like to know whether this is actually useful. So one of the tasks is to actually count the number of specific birds in a community. And when I was in Germany on sabbatical, that actually happened. So people had to, everybody, the whole community, could go out to certain positions in the park, certain places in the park, and then they would watch a tree for an hour, and then they would count how many birds would go to that tree and how long they would sit on the tree. And then they had a special thing about how when the birds flew away and came back, how they should count those. Like if they saw them come back, then it wasn't counted as a new bird. But if they didn't see it come back, then it's counted as a new bird. So let's see, you want to do that with these birds. I think those are parakeets from Australia. And then, given that task, how would you proceed? Well, of course, the proper solution you can see is going to be quite difficult already, right? Because the birds have different sizes, different shapes. The head rotates, so the shape would change dramatically. And just on that little branch, if you need to count how many birds are sitting on that branch, that turns out to be a non-trivial problem in a real scenario. when the sun is changing and shadows and things like that. But you may think that actually the first approach, at least as a rough estimate, would be to count the number of blue chests that we can recognize. Like this particular species of bird has lots of very strong blue chests. So maybe we can just look for blue and then group those pixels together, detect it as a blob, and then say, okay, now I detected a bird. At this second, there was a bird sitting, or there were 5 birds sitting on the branch. An hour later, there were no birds sitting on the branch. That kind of thing, that kind of application. Now, if you were to implement this in OpenCV correctly on your own computer, then you have an advantage over me because you can actually use the bounding box selection tools, the GUI tools, so that you can click and drag an image. But I can't actually do that with the Jupyter Notebook, so I have to cheat a little bit and pre-select the coordinates that I want for my color space, for my color model. Now, in order to figure out what part of the image I'm actually looking at, I'm drawing a rectangle by giving top left and bottom right coordinates in XY format, and then the color that I want to draw it. And that simply changes the image. So now we would go and I simply now select by looking at the coordinates where they roughly are for the top left and the bottom right corner of the rectangle that I want to use as a selector. So let's see where that is. Now, clearly here, if I look at a single pixel and then its neighbors, then there's going to be a small variation, right? The blue is not going to be just blue, which is why I select a region of the possible pixels, the pixels that belong to the blue chest. And then I want to come up with a test in order to test whether that pixel belongs to a blue chest or not, right? That's called a color predicate, because we're basically returning true or false, saying this pixel belongs to the chest of a bird, or this pixel does not belong to a chest of a bird. So now let's see. Actually, I want to draw the marker first. Assignment destination. See if I can copy this. So then here, this is the area that I selected for as a color predicate for the blue bird's chest. And that's a reasonable start for the calibration. And then I need to load the image again. So here are the seed coordinates, and then the minimum and the maximum. For the red, minimum red maximum, green minimum green maximum, blue minimum blue maximum. And then we can say, so red goes from 20 to 142, green from 106 to 195, and blue from 113 to 210. In this, in my seed part of the image. So now let's replace the colors and see what we actually detect. So we found 1947 407 pixel. So I go through the image, I get RGB for each pixel, and then I check if R is greater than or equal to the R minimum and R is less than or equal to the R maximum, and green greater than or equal to the green minimum, less than or equal to the green maximum, and blue, and then if it is, I replace it with the blue color, and I count how many pixels I replaced. So then here's the output, and actually if you look at the chests here, that's pretty good, right? Most of the blue areas of the birds, apart from this part here of that bird, most of those were actually recognized as belonging to the bird. But the problem is we also have some false positives down here. So I detect some blue birds here in this area, which are not actually birds. Chest of a bird. So then this is what I meant by calibrating colors. Then you're trying to look and find out what's the difference between these pixels here and these pixels there, because these ones I want, these ones I don't want. These ones would be true positives, so they belong to the class and they're correct, so they're true positives. Here would be a false negative. This one is classified as not belonging to the class, but it should belong to the class. So the algorithm says negative, but that's the false answer. It should be true. Here we have false positives. Right? Here the algorithm says they belong to a bird, but actually they don't. And then the rest of the background here, that would be true negatives. They don't belong to the bird class, and the algorithm says that they don't belong to the bird class. So now what people do usually is they extract, they're trying to do two things. One is to remove these outliers here and also to add more of these pixels so that the chest of that bird is completely selected, completely found. So now I can change with my seed markers. Here we can use a different seed now. Now I use, I said, oh, maybe instead of looking for blue, where I have some problems, maybe I can look for yellow. But you can see the yellow is much harder to detect. Like my seed area is this little rectangle here, and that one is clearly not enough. Like there's a lot of yellow here missing, false negatives, but also already some false positives. So different color test. So now here I made the blue area larger, and now I have fewer false negatives. This area now is found a little bit better, but also I get more false positives here. And let me check what this coordinate is here, and let's try and merge our color predicates. So let's try and do two areas, this area here and this area there. So in order to do that, I know. Okay, so I'll figure this one later. So now I want to write a new color predicate that merges the colors. Now I have them all as separate variables. Okay. So here we have two models. So R min, R max, G min, G max, B min, B max is equal to model 1, R1 min, R1 max, G1 min, G1 max, B1 min, B1 max, and then similarly for model 2, and now we just have to swap them, merge them. So if R1 min is less than R2 min, R min is R1. Actually, I just write it like this. R min is minimum of R1 min, R2 min, R max would be the maximum of those two maximums. Then we do that for the 3 channels. P1 max, P1 min, and then we're going to return R min, R max, G min, G max, P min, P max. So this will be a 6 feature color model. Right? We return 6 numbers in order to, or we use 6 numbers to describe the color. So now let's see drawing the second part. Sheet coordinates. That's the problem because I scale them on Google Colaboratory. So when I look up the coordinates in a drawing program or in the image, then it doesn't actually work. So we have images. So this would be 275 and 190. $275 and $190. So let's say this would be 80 left, 190 and 180. Let's try that. So 190, 180 I said, okay. Bottom right, so let's make it 210, 20, 210. And a little bit further down, so maybe 180, maybe 220. So now I just want to plot those in my image to see where they actually are. And I plot that in green. And I have to draw them. That's 0, 1. So these are all X cores, so they're in column format. So that would mean I get an array of top left 2, bottom right 2, and then I think I need to transpose it. So let's see. BR-2. BR. Let's go to. So here's the green one. So I need to move it a little bit to the right. Maybe 5 pixels and up about 10 pixels. So let's try that. Again, this is much easier if you have a GUI and you just click on it. So I set 5 to the right and quite a bit higher. Now we have that. Needs to be over another 5. Okay. Oh, some guesswork. Oh, it's YX, not XY. No, how come? this is X, this is Y, okay. So Y210 is too low. It should be 160. Oh no. No transpose here. Okay, yep, so that's better. Now we have X and 220, so make that 200. And our top is a little bit too high. 60, 70. Okay, so now we can add some more blue to it by using these colors here, and then we'll see what happens. I need to set the seed coordinates too. Here we can use slicing in the array, so I can immediately access that part of the image. And it would be better to have the color predicate as an array here, so that I can just iterate through them. But we're just going to go through the computation step by step, which unfortunately means that I have to do some copy and paste here. Then we get our min, our max, gmin, gmax, bmin, bmax is equal to merge models. Right, that's what I call merge thresholds. So first one is R min, R max, G min, G max, B min, B max, and the second one So now we have very solid color model, right? We hardly have any false negatives, just here and here a little bit. But our problem is now the number of false positives increased a lot. We also get them on the beaks here now, which we didn't want, so on and so forth. And this is the general dance that you have to do if you're trying to use color detection in any kind of intelligent application or robot application. It's actually very difficult in natural lighting to get this to work. It seems very it's very seductive because you think they should be quite easy to implement. For example, to count if you do image processing in order to detect forests or something like that versus prairies, then everything is just green, and then the different types of greens are trying to count the number of trees of a particular type. It turns out to be quite hard, much harder than you think. So it is the easiest way. You can see we can just build a classifier from scratch, not even using any of the OpenCV functions, in a couple of minutes. But to get it to work correctly is a lot. Calibration is a huge problem. So initially we tried to use that for RoboCup, the Humanoid League. We had all color-coded environments. In 2012 then finally the state-of-the-art in vision was strong enough in the competition that teams weren't even using the color anymore. So we could get rid of it. So now we have white goals, white field lines, and white balls, and the green carpet, and that's it. There's no color in the environment anymore. What I was trying to demonstrate is the two types of errors that you have in any vision system, in any classifier, not just vision system, but anything that responds with yes or no. Does this belong to this class or not? These classifiers have always two types of errors. There's false positives, which means that you say this is part of the chest of the bird, but actually it's not. And false negatives, where your algorithm says that it's not a bird, but in fact it is a bird. And often the trick in a successful application is to find the right balance between those two errors, because often the errors, the domain is such that false positive error may be very, very bad, whereas a false negative may be tolerable. So in this case, you want to tune your algorithm to allow for more false negatives, because false positives would be a huge problem. So for example, if you are implementing a intelligent system to check the engine on a 747, whether it needs maintenance or not. So you get all the data about the engine, how many hours it has flown, what the temperature was, what fuel was used, any emergency maneuvers that the pilot had to do. All of this information is fed into your system, and then you want to print out a message saying, yes, this plane should not fly. We need to take the engine apart and rebuild it. Now, this is a lot of work, right? And costs a lot of money. So the company is interested in reducing the amount of unnecessary maintenance that it does. But in such a domain, it's clear that if you have a false positive, and depending on how you ask the question, if you have a false positive and you say, yes, this engine must be maintained, and they pull it off the plane and they take it apart and they find out nothing wrong with the engine. Then they put it back together, and then some passengers will have been delayed, or they needed to hire an extra plane or lease an extra plane. That is, of course, not ideal, but a false negative where your system says, no, the engine is perfectly fine to fly, and then the plane crashes, that would have vastly different consequences. It would be much worse. So for such a system, you really have to tune it such that it's impossible to get a false negative, or almost impossible to get a false negative. Similarly, with false negatives, what other example? Medical diagnosis, right? You have a classifier that says whether somebody is cancer-free or still needs medication. If you say that he doesn't need medication anymore, but the cancer comes back, then that person will die. Very, very bad outcome. The other side, of course, cancer medication is non-trivial. It has a huge impact on the body. It's very stressing on the body, but it's better than having the cancer run rampant, not being checked. Or if you say that cancer is spreading, then the doctors can do additional tests in order to try and confirm or disprove that particular hypothesis. So let's have a look at ball detection. Actually, I need to set up the image for a slide. I'll show the image here. Ooh. Okay, now I really added too many blue colors. No slide. So we have that. So here's our picture. With our rectangle. Minimum maximums extracted for red, green and blue channel and then replaced. Then we have the Z coordinates. And then we merge thresholds. And now we have this output with more false positives, but fewer false negatives. So let's try that on a different type of image. So here, this would be the same, it's one picture with many balls, right? But it would be the same as detecting a single ball in many different positions. I just took that picture because that makes it a little bit easier to see. And let's see what happens if we pick color predicate here. Then let's see what we get. So here, similar problem, right? The balls are detected okay with this particular marking here, but we also have lots of ghost balls here in the concrete divider, also in the ground here, and the watermark also looks like the ball. So that means it's problematic to use that approach in order to try and find the balls in the image. So then at that point, in the mid 1990s, early 2000s, researchers were starting to look and see what the major disadvantages of the RGB color space. And the problem is that it's very susceptible to the brightness of the scene. So if you have a light shining onto the playing field and then you have another area in the shadow, the RGB values will dramatically differ. So then the idea was that all we need is a better color space, maybe HSV, maybe YUV, maybe something that some researcher found or proposed. And there were lots of different color spaces that people proposed. Turns out they're all bad, really. None of them work well enough. Some of them are better in one kind of domain under particular lighting conditions, but in general they all suck. So it took us about 3 years to figure this out. One of the solutions or one of the there were many different approaches that have been used. HSV, YUV cosine transform, which models the RGB color as two angles, so and the distance, so polar coordinates basically in 3D. and a lot of other ones. We designed one where we used a 12 color predicate that used red minimum, green minimum, blue minimum, and the maximum, and then also the red minus green, red minus blue minimums and maximums. The trick was to come up with a color predicate that was expressive and allowed us to detect our obstacle objects accurately with few false positives and few false negatives, but that was also still able to be run in real time. So you wanted to have your color predicate to run very quickly, because you would look over the entire image, so every pixel would be run against your color predicate. But on average, none of them really work very well. Another improved color space that was proposed was the normalized RGB space, where we normalize the size of the RGB vector to be length 1. So our color that we actually read in, normalized red, would be red divided by red plus green plus blue plus 1. And green would be green divided by red, green, blue plus 1. And blue would be red plus green plus blue plus 1. The plus 1 here actually is only there in order to avoid that we have to check for division by 0. Otherwise, if I had a black pixel, 0, 0, 0, then red plus green plus blue would be 0, and I would get a division by 0. So we add 1 to it. That is slightly better than just using red minimum and maximum, the 6 color predicates, but in reality it doesn't give you much more. It's not powerful enough to really do a large soccer playing field. If you have a small table where you need to detect an object on, then it works quite well. But for a 3 by 4 meter playing field with spotlights, shadows, windows, doors opening, windows opening and closing, curtains being drawn, this also will not work. But we can try and use the RGB normalized RGB color model here on our image and see what the result is. So I calculate the sum and then generate a new pixel that is the fraction multiplied by 255 to scale it from 0 to 255. And then this gives me my normalized color image. Then I can look for the minimums and maximums in the normalized RGB color space, and then we can plot that. So here's our normalized color space. Using this seed, it actually performs not as good as the previous system as far as detecting true positives. So we have fewer true positives, but we also have fewer false positives. So depending on your application, this may be better than just using the straight red, green, blue color space. Nowadays, I think any kind of computer vision application, looking for colors first is the wrong approach. You need to look for shape, location, predicted position of the objects, and then if you think this is a circle at a position where I expect the ball to be, and it has the right size and it doesn't look like an ellipse, and then at the very last instance you can check, is this a yellow tennis ball or maybe an orange soccer ball or basketball? That kind of question you can ask your color predicate, because at that point you're already 99% sure that this is the ball that you're looking for, and it's just one additional test. And then your color predicate can be much wider, right? Can be much more inclusive, because if it's circular and in the position where you expect the ball to be, there's a very good chance that this already is a ball. So you can be a little bit lenient in your color predicate. It's not like going for every pixel and saying, is this a pixel that belongs to a ball? Is this a pixel that belongs to a ball? In that case, your color predicate has to be a lot more precise. And of course you can add multiple regions to get a slightly improved color predicate. So here's our color difference model. That's the one that we developed and used on our soccer playing robot for a long time. We extended the RGB color model, which does a pretty good job checking the brightness of things, but doesn't check the color component sufficiently, and added red minus green, red minus blue, and green minus blue channels, which give us an extra 6 features. So now a pixel is actually a 6-dimensional object as opposed to 3 dimensions, not just RGB, but also R minus G, R minus B, and G minus B. This color model we used because it was we used it 1998, and there we were running it on a Pentium processor that had the first set of SIMD instructions, and you could do 32-bit subtraction and ANDs, and like bitwise operators, and add and subtract very efficiently over huge parts of the image in parallel. And we did some bit fiddling with it. Nowadays nobody really cares about those optimizations anymore, because modern CPUs can now execute more complex instructions even in 1 clock cycle, or a superscalar in less than 1 clock cycle. But our model ran very quickly because we only needed a single subtraction and an AND to check all 6 color channels. So RGB and then the difference channels we could all check by doing a single subtraction on 32 bits and then an AND. And then using the SIMD instructions we could do that in parallel. So that proved quite powerful, quite good. And now sometimes I still use it if I have a very simple problem to work on, but in reality it is we now have better methods that are running slower, but we have the CPU power to still use them at real time there. So let's see what that image looks like. So here in NumPy I can also calculate those pretty quickly because the NumPy arrays have the vectored subtraction of arrays and channels. So that works quite fast too. And then let's see what it looks like. Oh, I forgot to show the image actually. So here's our RGB difference channel using the same seed region. It does a much better job. We have a couple of false positives over here, but they're very small. So this part, I'm pretty confident on this particular area you will be able to detect the yellow tennis ball. If you do a little bit more tuning, then this would work. Yeah, no, we have that seed. We don't have any, no false negatives. It's a false positives there anymore. So what was I using there? Yeah. So here we can look at the gradient, which means the derivative in the x and the y direction of our image. Because if you want to use structure, then instead of looking for colored pixels, you look for edges, which are basically differences between neighbors in intensity or color space. So then you'd be interested in the gradient. No, sorry, this is different. Yes, we're interested in the gradient, but here you can see that the color conversion from a colored block to a grayscale is not so simple, because here it's the same brightness value in the particular channel. So here R goes from 0 to 255, here green goes from 0 to 255, and here blue goes from 0 to 255. So you would expect the perceived brightness to be the same along each column, but you can see that that's actually not true, right? The blue, the black here and the red, and especially this blue area here looks darker than the green one here. So that's what the HSV color space is trying to compensate. It's looking at how humans, trying to model how humans perceive color, and the brightness of colors in particular. Sorry, not from RGB to grayscale, of course. So intuitively, you would end up with a conversion that just says red plus green plus blue. The average intensity of the pixel in the 3 channels is the grayscale of the image. But that is not actually true, because here if you compare along the columns, then green here looks a little bit darker still than the corresponding red. The blue feels darker the entire range. So instead, there's a particular formula, and that is due, that difference in intensity perception is due to the fact that the human eye is much more sensitive to the green. So grayscale. To do the conversion, so that it more closely matches the perception of a human, the correct formula is 0.3, and they even have to the hundreds. The weights. So here, if we calculate the average, we gave each color channel 33% of the weight. But since humans are more susceptible to green color, the green should have a stronger influence. So the correct formula for conversion for human perception. Now, if you do this with your robot, it doesn't really matter because your robot doesn't see any colors anyway. But if you want to present the image to the user in grayscale and you want to make that as realistic looking as possible for them, you would need to use the following conversion, where you have 0.299 times red plus 0.587 times green plus 0.114 multiplied by blue. So this is a more closely matches human perception, this conversion. And then you can run edge detection or something like that. That's usually what you're supposed to do. But I often cheat when I need a grayscale image. If you look at it, the green channel here, the weight of the green channel is 0.587. So it's about twice as important as red and about 5 times as important as blue. So when I want to do the conversion, I simply take the green channel. I don't even bother with red and blue. Of course, that works well in natural scenes, the kind of scenes that our robots need to interpret. If you are drawing something with a lot of blue lines, like artistic design or something, then of course you would need to do a more better conversion. But to get started, to just take the green channel works surprisingly well. So here, this is the conversion just using the green channel. And I can also, it's weird why, oh, I cannot do figures, but let's do the proper grayscale conversion, just out of interest to see what the image, how they look different. So I want a new image. That matches image.shape and is all zeros. Use American spelling. Okay, then actually in NumPy we can do that, and then you would write a for loop for y in row, for x in column, but actually using the NumPy functions you can do that a lot faster, because I think the new image is equal to image dot 0.299, 0.587, 0.114. So we calculate the dot product of every pixel, which is RGB, with the values of our weights. Let me see if that works. Yep. Okay. And then I need to convert it into integers. No. S type. Yeah, now it looks like integers. And then we want to compare them. One row, two columns, first frame. So let's show the image green. CMap is equal to gray. Color map is equal to gray. And that would be image 2. Okay, let's see. Why is that so small? 122, sorry. What were the weights again? 299, 587. That should be set title. Set title. So here you can look at the difference between those two. And for detection with our robots, usually there's very little difference. But of course, extracting just the green channel is a lot faster than doing the conversion. Here's the code for it. So yeah, the balls are a little bit brighter in this conversion because yellow consists of red and green. So there would be a strong green component in the yellow balls. So let's have a look at the motion picture. Oh, not found. Okay, good. Then that's it for today. I need to figure out exactly what picture I wanted to use for the blob detection. So the computer vision class on Wednesday at 9 a.m. If you want to join that, it will take part in class. Otherwise, I will see you on Monday again. Okay, so that's the end of the class.